Hello, and welcome to The Sleepy Scientist. Settle in, let shoulders loosen, and allow the day to drift to the edges. Tonight's quiet companion is the geometry of nothingness, a slow walk through the hidden shapes of emptiness and the calm rules that guide them. Before the journey begins, a small curiosity. Where are you watching from this evening? What city, coast, or countryside keeps you company right now? If gentle, accurate science helps you unwind, a soft tap on like and subscribe is always appreciated, and a warm thank you to those already subscribed for keeping this space peaceful and curiosity-friendly. May this episode be just interesting enough to rock the mind to sleep, and if wonder keeps eyelids open a little longer, at least the thoughts that wander will return carrying the quiet outline of new ideas. So, as the room settles and the breath evens, here is a question to hold like a smooth stone in the palm. Can nothing have a shape at all? Nothingness sounds like an empty word, yet in science and mathematics it wears many careful meanings. In philosophy, nothingness is absence, no matter, no space, no time, no properties. In physics, the vacuum is not truly empty. It is a stage built from fields, a quiet surface where ripples can appear. In mathematics, emptiness can mean the empty set, the zero that anchors a number line, or the bare points and distances that make a space before anything fills it. The journey ahead traces how these senses of nothingness gain structure, and how geometry, rules of distance, angle, and connection, can describe a silence that is not simple. The pace will be unhurried. Begin with the earliest debates about the void and why thinkers argued so carefully over what could not be seen. Then move to the invention of zero and how placing a mark for nothing reshaped counting, calculation, and the way coordinates give even emptiness an address. From there, step into Euclid's calm garden of lines and triangles, the axioms that sketch a flat world, and the single stubborn idea about parallels that opens the door to curved spaces. Curvature arrives next, spheres where straight paths circle back home, and saddle worlds where parallel lines drift apart like old friends taking different routes through a park. This leads naturally to Spacetime, where gravity is not a pull but a bend, and motion follows the quiet instruction of geometry. Closer still, the quantum vacuum murmurs with possibility, a restless calm that remains gentle at human scales. Beyond angles and lengths lies topology, which cares less about sharp corners and more about what stays connected when shapes stretch and breathe. Symmetry enters as the grammar of laws, the calm patterns that promise conservation and balance. To keep the senses soothed, art and architecture offer a parallel path, negative space and minimal forms that prove emptiness can cradle meaning. Finally, widen the view to the cosmos, horizons, expansion, and the question of whether the universe is finite yet boundless, like a long walk that returns to its own beginning. All along the way, each idea will be set down slowly and simply, with images that rest the mind and facts that hold still. If attention wanders, it will always be easy to find the path again. The goal is modest and deep, to feel by the end that even in the quiet places where there seems to be nothing at all, there is a shape to the silence, and that understanding it brings a gentle kind of peace. Picture a quiet room at dusk. The walls are plain, the air still, and the silence feels almost tangible. The room's boundaries make the silence audible to the mind. Without edges, the hush would be harder to notice. Philosophers began here with an intuition like this. Perhaps what is called nothingness is not a thing, yet the frame around it gives it shape. From that gentle starting point, arguments grew, some bold, some cautious, about whether the void exists at all and why it matters. In the world of ancient Greece, one voice stood suspicious of emptiness. Parmenides argued that what truly is must be whole, unchanging, and indivisible. If non-being is literally nothing, it cannot be spoken of, cannot be thought, and certainly cannot exist. Change would require something to arise from nothing or vanish into nothing, which reason forbids. motion would demand gaps, and gaps would be a kind of non-being. Better, he thought, to trust the razor of logic. Reality is a solid completeness. Motion and the void are illusions that sense whispers but reason denies. The result is austere, like a stone sphere in the mind. No holes, no cracks, no empty space where mischief could begin. Across the same landscape of ideas, another current moved in the opposite direction. The atomists, associated with Leucippus and Democritus, proposed that reality consists of indivisible atoms moving through empty space. The void is not a strange nothing to be distrusted. It is the necessary backdrop that allows atoms to shift, collide, separate, and weave the visible world. Without a void, motion would be impossible. Everything would be packed with no room to rearrange. Where Parmenides sealed the world into a seamless whole, the atomists pried it open. Their void is not a substance with properties. It is the absence that grants possibility, much like the room whose open floor lets a dancer move. These two visions could not be more different. One insists that pure reason forbids non-being. The other insists that everyday change cannot happen without empty spaces where matter is not. The tension between them shaped centuries of debate. It also offered early glimpses of an idea that later science would refine. Sometimes the stage matters as much as the actors, and sometimes the stage is a kind of structured nothing. Aristotle entered this conversation with a careful skepticism toward the void. He examined motion and argued that movement requires a medium, air, water, or some continuous substance that can be displaced and offer resistance. A true vacuum, he reasoned, would lead to paradoxes. With no resistance, speed could become unbounded. The very relations that make motion intelligible would collapse. While the famous phrase, "nature abhors a vacuum," is Latin, and took its popular form later, it captures the spirit of his view. For Aristotle, the cosmos is a plenum, a full, continuous world in which bodies move by pushing and yielding, like oars through a dense sea. Space is not a container waiting to be filled. It is the order of relations among bodies already there. After the classical period, the thread did not break. It changed hands. Late antique thinkers such as John Philoponus challenged parts of Aristotle's physics and argued that motion could persist without a surrounding medium, seeding ideas that later became impetus theory. In the medieval Islamic tradition, philosophers and theologians read, critiqued, and extended Aristotle. Some currents in Kalam explored atomistic notions quite different from Democritus, while major figures such as Avicenna and Averroes wrestled with continuity, place, and the possibility of a void. In medieval Europe, scholars such as Jean Buridan and Nicole Oresme developed impetus ideas that loosen the tie between motion and the medium, creating conceptual space for thinking differently about vacua. Debates ran through universities, monasteries, and courts. Could God create a vacuum if desired, even if nature avoids it? The question linked metaphysics, theology, and physics in a single long braid. Centuries later, early modern experiments with mercury columns and barometers would carefully carve out pockets of low pressure and show how the weight of air behaves. But the conceptual groundwork for taking empty space seriously had already been laid by persistent argument. It is easy to forget that while Aristotle's plenum dominated, another Greek tradition quietly entertained emptiness. The Stoics, for instance, imagined a finite, coherent cosmos suffused with a living, breath-like principle, yet they allowed for an unbounded void outside the cosmos, a kind of vast outside where nothing structured resides. Their cosmos floats in emptiness, though the inside remains full. Even here, emptiness serves as frame, the way a margin gives a text breathing room. Far from Greece, other traditions gave nothingness an entirely different tone. In certain strands of Buddhist philosophy, especially in teachings on emptiness, the word does not mean a literal vacuum, but the lack of fixed independent essence in things. Forms are empty of inherent nature, and emptiness is not a bleak absence, but the condition that allows dependently arisen patterns to appear at all. The well-known line that form is emptiness, and emptiness is form points less to a physical void than to the idea that things are open, relational, and without a solid core. In Taoist texts, there is a famous image of usefulness residing in what is not there. The wheel works because of the empty hub. A room is livable because of the empty space within walls. The insight is practical and serene. What is absent can grant function, clarity, and quiet. None of this settles the physics of vacua, but it widens imagination and softens the starkness that the word nothing can carry. Step back, and a pattern emerges. For some thinkers, nothingness is a contradiction in terms, a boundary where thought must halt. For others, it is the necessary backdrop for change and motion. For still others, it is a cue to look for relations instead of essences, or to appreciate the usefulness of clear space. Across these views, emptiness is never simply blank. It is either banned by logic, enlivened by atoms, structured by relations, or honoured as the margin that lets meaning stand out. The quiet room at the start returns. The silence is defined by the walls, by the doorway, by the open floor. Remove the frame, and silence becomes harder to notice. Why did this matter to later science? Because every theory needs an account of where things are and how they can move. If space is a plenum, forces and motions must be explained as interactions within a filled medium. If there is a void, motion can be the travel of bodies across emptiness, and forces can act at a distance, or geometry itself can guide them without a medium in between. The willingness to treat emptiness as something describable, not merely mystical, helped make precision possible. When a thinker pictures a void, the mind begins to ask practical questions. How would pressure behave? How would light travel? How would the path of a falling object be traced? Those questions nudge thought toward measurement models and carefully drawn diagrams. There is also a gentler truth. Ideas about nothingness trained habits of attention. Philosophers became careful about language, distinguishing absence from negation, possibility from contradiction. They learned to watch how a single assumption, no void or necessary void, ramifies through an entire worldview. That discipline of tracing consequences would later serve mathematics and physics well. The conversation about nothingness placed a quiet demand on reasoning. Define terms, test intuitions, and keep an eye on the frame as much as on the picture. If emptiness can carry structure, then the mind begins to wonder how to describe that structure without stuffing the emptiness full of things. What is the most economical way to mark a location, to speak of distance, to compare directions? The philosophical debate about nothingness does not answer those questions, but it prepares the ground. It encourages the thought that even the barer stage might have rules, that the space around things might be mapped without cluttering it, and that clarity can ride on sparse lines. Return once more to the image of the quiet room. The usefulness of the space is not in what fills it, but in what does not. A doorway marks a threshold, a window frames a view, and the open floor invites a step. Shape appears because there are edges. Direction matters because there are boundaries to cross. The calm recognition that emptiness can be articulate without ceasing to be empty opens the door to a new kind of description, one that prefers clean definitions, spare marks, and measured relations over metaphysical declarations about fullness or lack. That is the gentle bridge from the history of ideas to the language of measure. To speak neatly about emptiness, a mind reaches for a symbol that marks absence, for a point that anchors a line, for a way to count without clutter. Reason finds it comforting to place a cross where directions meet, to call the crossing the origin, and to let distances stretch quietly outward along straight paths. With such tools, the hush of the room becomes traceable without losing its calm, from words about nothing to numbers that measure it. Imagine standing at the edge of a still pond at night. The water is dark and untroubled, and every ripple that appears travels outward from a quiet centre. Zero plays that role in the landscape of numbers. It is not a splash of quantity. It is the calm place from which quantities radiate. To understand how this calm came to be, it helps to wander back through time, where practical scribes, thoughtful astronomers, and patient philosophers slowly learn to mark nothing with something. In ancient Mesopotamia, mathematicians wrote in clay with a base 60 system, elegant and efficient for astronomy and trade. They faced a practical problem: how to distinguish, say, one followed by an empty place from one followed by a filled place. Their solution was a placeholder symbol, often a pair of small wedges, to mark an absent digit between other digits. It was not yet zero as a number that could stand alone. Think of it as leaving a deliberate blank in a line to keep the rhythm, a pause that keeps the beat steady. The idea that nothing could be written as if it were something had arrived, but only as a position marker. Centuries later, on the Indian subcontinent, a deeper step was taken. Mathematicians there treated zero both as a placeholder and as a number with its own behaviour. Brahmagupta, writing in the 7th century, described rules for zero in arithmetic. How adding zero changes nothing, how subtracting zero leaves a quantity as it is, how multiplying by zero returns zero. Some rules, such as attempts to divide by zero, were not yet aligned with modern understanding, but the conceptual leap was clear. Zero could be part of the arithmetic conversation, rather than a silent mark between other marks. Once nothing could participate in calculation, a door opened to cleaner algorithms, clearer bookkeeping, and a robust positional system. From India, the numerals and the zero travelled through scholars writing in Arabic and Persian. The word for empty, cipher, lent its sound first to medieval Latin as zephyrum and then to zero. Scholars such as Al-Khwarizmi explained calculation with these numerals, and merchants appreciated how quickly accounts could be kept. The benefits were practical and immediate: fewer symbols, faster arithmetic, and fewer opportunities for error when dealing with long columns of numbers. In medieval Europe, this system took hold slowly. Some cities even restricted the new numerals for official records, worried about fraud, since smooth curves were easier to alter than tall Roman strokes. Yet convenience is patient and persuasive. With the help of teachers and texts, Leonardo of Pisa, often called Fibonacci, being a notable voice, account books, workshops, and universities eventually welcomed the new marks, including zero, and the everyday world of calculation changed tone. Once a culture accepts positional notation, zero becomes the quiet ruler of place. In such a system, a digit's value depends on where it stands. A 2 in the ones place is 2, a 2 in the tens place is 20, a 2 in the hundreds place is 200 hundreds place is 200. Zero keeps those places honest. Drop a zero, and a number shifts meaning. Insert 1, and an empty column shows its weight. This makes zero a positional tool, but it is also a conceptual anchor. As an additive identity, zero leaves a number unchanged when added. Saying add zero is the same as saying do not disturb. Multiplication shows a different personality. Any quantity multiplied by zero becomes zero, like a ripple smoothed back to stillness. These simple behaviours, easy to state and remember, make lengthy calculations reliable, which is why merchants, astronomers, and engineers embrace them so readily. Now picture that still pond again, but this time lay a slender stick across it to mark a straight line. Place zero at the centre, and let positive distances extend to one side and negative distances to the other. This is the number line, a mental instrument so familiar that it feels inevitable. Yet it represents a significant shift. Nothing now has a location. Distances are measured from zero, and direction becomes part of the story. Extend this idea to two lines that cross at right angles, and the calm point where they meet becomes the origin of a plane. With a pair of numbers, every point can be named. With 3 numbers, every point in space can be described. The origin is the pond's centre, Coordinates are ripples carrying information outward. This way of locating nothing did more than help draw neat graphs. It clarified the meaning of negative numbers, once treated with suspicion because one cannot have a negative flock of sheep or a negative pile of grain. On the number line, negatives are simply positions on the opposite side of the origin. Depths and temperatures below freezing found a natural home. Symmetry bloomed. Move a step to the right, and there is a mirrored step to the left. Climb above zero, and there is a mirrored descent below. The coordinate plane repeated that symmetry in two directions, and geometry fused with algebra in a new intimacy. Equations became shapes. Shapes became equations. All of this rests on a point named zero. There is yet another way in which zero gives structure, and it lives in the idea of approaching. Imagine releasing a small leaf on the pond and watching it drift toward the centre. The leaf may never quite touch the exact point, yet it can come as close as desired. The language of limits captures this feeling. Mathematicians learn to speak about quantities that approach zero, to measure how functions behave near that quiet boundary, and to make precise the idea of arbitrarily close. Ancient geometers had intuitive and rigorous methods for squeezing areas and lengths. Think of the method of exhaustion. But the careful language of limits matured much later, especially in the 19th century, where definitions use small positive distances from zero to trap behaviour and make it reliable. Limits allow motion in thought without losing control, a kind of safe glide toward nothing. The notion of the infinitely small has a long and adventurous history. Philosophers in antiquity wondered whether space and time are endlessly divisible, or built from indivisible units. In the early modern era, mathematicians such as Cavalieri spoke of indivisibles, and Newton and Leibniz spoke of quantities so small that their squares and products could be neglected. These infinitesimals, as they were called, gave a nimble language for describing change, slopes, and areas. Later, to secure firm foundations, analysts preferred limits, which make no commitment to an actual infinite smallness, but instead use the approach to zero as a measuring stick. In the 20th century, rigorous systems were even built that allow infinitesimals to exist consistently, showing that the old intuitions can live alongside the precise language of limits. Whether by approaching zero or by imagining tiny but non-zero steps, the mind gains a fine-grained way to talk about edges, corners, rates, and smooth curves. Why does this matter for the shape of emptiness? Because zero teaches the hands how to hold nothing without crushing it. As a placeholder, it preserves meaning by keeping locations in order. As a number, it behaves predictably, giving arithmetic a neutral element for addition and a sink for multiplication. As the origin, it offers a reference point from which directions and distances gain clarity. As a boundary approached in limits, it provides the scale for refinement, letting descriptions become as delicate as needed. With these roles working together, empty stretches of line, plane, and space can be described without being filled. The grid that names points does not weigh down the space it maps. The axes that cross at zero do not clutter the plane. The concept of near zero sharpens understanding without introducing substance. Spend a moment with a radial picture, concentric circles centered on the origin, each circle a path of equal distance from the calm point. This is another language for the same clarity, polar coordinates, where a point is described by how far it is from zero and by the angle it makes with a chosen line. Again, zero is not just an absence, it is the centre of reference. Whether the grid is square or radial, the purpose is the same, to let emptiness carry structure without losing its quiet. The mind learns that order can exist without filling every corner, that naming points does not require piling objects into them, and that the most informative point of all might be the point that marks nothing. This quiet confidence transforms how problems are solved. Curves are easier to study when distances from zero are clear. Balances are easier to keep when gains and losses sit symmetrically around the origin. change becomes easier to quantify when small steps measured against zero tell how steep a climb or how gentle a slope. Whether drawing a simple line or describing a complex motion, the presence of zero acts like the silent conductor of a slow orchestra, keeping time, aligning entries, and making harmony from separate parts. In that light, the history of zero is more than a tale of symbols. It is a story about learning to make absence useful. From a placeholder among wedges to a number with rules, from a merchant's tool to a scholar's anchor, from a quiet dot on a line to the crossing of axes that name a world, zero has given language to the places where nothing is. The still pond has a centre. From that centre, ripples carry information outward, clear and calm. If numbers can chart nothing, lines can sketch its rules. Imagine an empty garden smoothed flat by rain. The ground is quiet, the air is still, and you place one stone, then another, each set with care to make a path. Euclid began in a similar spirit, arranging a small collection of simple rules and letting them guide everything that followed. The goal was not to fill the garden with decorations, but to let a few well-placed stones define a landscape. With restraint and patience, those stones became the foundations of geometry. Euclid gathered earlier Greek mathematics into a work called the Elements. At the heart of that work sit definitions, postulates, and common notions, which together serve as the starting kit. A point, he says, is that which has no part. A line is breadthless length. A straight line lies evenly with the points on itself. These are not measurements but clarifications, a way to keep the imagination from wandering too far. After the definitions come the postulates, requests about what constructions are allowed with straight edge and compass. Draw a straight line from any point to any point. Extend a finite straight line continuously in a straight line. With any centre and distance, describe a circle. Right angles are all equal, and then a final, more intricate request about how lines behave when a third line crosses them. Each postulate is modest in tone, but together they fix the rules of play in the empty garden. Alongside the postulates sit the common notions, broad and almost philosophical. Things that are equal to the same thing are equal to each other. If equals are added to equals, the wholes are equal. If equals are subtracted from equals, the remainders are equal. Things that coincide are equal. The whole is greater than the part. These statements do not mention points or triangles. They speak to equality itself. They are the background hum that keeps every careful step in tune. From these seeds, Euclid grows lines, angles, triangles, and circles. Congruence enters naturally. If two figures can be made to coincide, edge to edge, angle to angle, then they are the same in shape and size. He proves that triangles with two sides and the included angle equal are congruent, which means that when pieces match, holes match. Distance is the length of a segment, angle is the opening between rays, and right angles stand as the stable benchmark. Step by deliberate step, he builds a toolkit. Bisect an angle, erect a perpendicular, construct an equilateral triangle, draw a circle through a point. None of these is dramatic. Each is a quiet, dependable gesture. The most famous and fragile piece is the parallel postulate. Stated in Euclid's own way, it says this: if a straight line crossing two other straight lines makes interior angles on one side sum to less than 2 right angles, then those two lines extended will meet on that side. It is a mouthful, but its spirit is simple. It sets a rule about the fate of lines that lean toward each other under the inspection of a crossing line. A shorter, later form known as Playfair's axiom captures the same content. Through a point not on a given line, there is exactly one line parallel to the given line. This is the hinge on which many familiar truths swing. From it, follow the comforting certainties of flat geometry. The angles of a triangle sum to 2 right angles. Similar triangles behave as expected, and shapes at a distance can echo shapes up close. The wonder of Euclid's approach lies in how little is assumed and how much is achieved. He does not start by measuring, he starts by proving. Proof, in this garden, is a kind of meditation. Begin with the stones already placed, definitions, postulates, common notions, and take a single step that follows necessarily, then another step, and another, never rushing, never skipping. A diagram helps the eye, but the reasoning carries the weight. When a conclusion arrives, it arrives with a calm of inevitability. The Pythagorean theorem becomes not a rumour about squares on sides, but a consequence that cannot be otherwise once the earlier stones are in place. This discipline, proof as patient building, gave later science a model for how certainty can grow from silence. Still, questions linger around the edges of the garden. Euclid's definitions are clarifying but not fully rigorous by modern standards. What does it mean, precisely, for a line to be breadthless, or for two figures to coincide? He sometimes relies on the picture, sliding a triangle in the mind to compare it with another. Later, mathematicians noticed hidden assumptions, that circles drawn with certain radii will actually meet, that a line can be extended indefinitely without obstruction, that between 2 points there is a third. None of these is absurd, but none is explicitly stated. Further, the parallel postulate feels different from the others. It is longer, more conditional, less obviously simple. For centuries, geometers tried to prove it from the remaining postulates, hoping it was not truly independent. Those attempts always found themselves back in the same place, either smuggling in something equivalent to the very statement they wished to derive, or discovering that a coherent geometry could be built in which the postulate does not hold as Euclid said. That failed quest turned out to be a gift. It showed that Euclid's garden was not the only peaceful place where geometry could grow. But within his boundaries, the harmony is striking. Congruence gives trust. Match a side here to a side there, and a triangle's shape locks in. Distance behaves steadily. Rulers do not warp as they move, and a straight line is the path of shortest length between points. Angle measure is stable. One right angle is the measure for all, and equality of angles transmits through constructions like light through clear glass. This consistency makes calculation possible without clutter. It lets a surveyor divide land reliably, and an architect set a wall at a true square. It lets a navigator trust a bearing, and a builder trust a blueprint. Even when later methods generalized or replaced particular techniques, the ethic remained. Begin with simple allowances, justify each step, carry conclusions gently forward. Reading Euclid can feel like walking a quiet colonnade. Propositions follow one another with a rhythm, each resting on prior supports. At times there is a small flourish, a clever construction that unlocks an angle or a length, but even those flourishes are restrained, the way a garden path may turn just enough to reveal a new view. The serenity is not an accident. It is the form that reason takes when it tries to rely on very little. In that serenity, students learned a habit of mind. Do not assume more than you must, say what you mean. When two things are equal, say why. When two lines are parallel, show how you know. This habit trained generations to expect transparency from arguments in mathematics and beyond. Even the rough edges teach. Where Euclid leaned on pictures, later thinkers supplied axioms for betweenness, continuity and incidence, making explicit what had been implicit. Where congruence needed firmer footing, they gave it careful rules. Where distance and angle demanded a consistent metric, they defined it precisely. This tightening does not dim the shine of the elements. It reveals the lasting value of the original vision. Start small, keep the rules simple, let the structure do the work, and there is that hinge again. The parallel postulate ties the garden to a particular flatness. If its wording feels heavier than the rest, that is because it pins down a behaviour that is not forced by logic alone. Reject or alter it, and the garden shifts its shape. Triangles could sum to more than 2 right angles, or less than 2 right angles. Parallel lines, depending on the rules, could multiply or vanish. The paths of shortest distance might curve not in the drawing, but in the very definition of straightness. None of this is a flaw in Euclid's design. It is a reminder that a few careful stones can define one beautiful landscape among others. For the moment, linger in the calm he built. Points without parts, lines without breadth, planes that stretch evenly, circles obedient to their radii, angles measuring openings like steady gates. Congruence keeps shapes honest. Distance keeps steps consistent. Proof keeps the pulse slow and certain. In a world that often hurries, Euclid's pace invites deep breathing. One lemma, one construction, one conclusion, and then quiet satisfaction. Everything in this garden rests on agreements small enough to say in a handful of lines and strong enough to hold centuries of thought. The achievement is not only the theorems themselves, but the experience of seeing them unfold from almost nothing. From definitions and a few allowances, space gains form. From fairness in equality, measurement gains trust. From a single hinge about parallels, the entire mood of the plane is decided. With that mood set, a final gentle thought rises like a question placed neatly on a stone. What if parallel lines refuse to stay apart, or ever meet? Imagine space as a vast fabric laid out beneath starlight. In some regions, the cloth lies flat, threads running straight and true. In other places, it swells like a gentle dome, or dips like a saddle left out in the rain. Walk across it with a careful stride and a surprising truth appears. The rules that seemed universal in a flat field bend gracefully with the fabric. Distances follow new instincts. Straightest paths curve, and the quiet sum of angles inside a triangle refuses to be the same everywhere. Begin with a sphere, the most familiar curved world. On a globe, the straightest possible routes are not the horizontal lines painted by a classroom ruler, but great circles, the largest circles that can be drawn on the sphere's surface, whose centres match the sphere's centre. An equator is a great circle. A meridian that runs from pole to pole is a great circle. If two cities lie far apart, the shortest journey between them hugs a great circle path, even if the route looks oddly bowed on a flat map. These paths are geodesics, the sphere's version of straight lines. Walk them, and the feet feel the motion as straight and steady as a line on paper, though an observer outside the sphere sees a curve. Triangles on a sphere carry a soft, wonderful secret. Draw one side along a great circle, then another, then a third, letting the sides meet neatly. Add the interior angles. Instead of the familiar sum of 180 degrees, the total becomes more than 180 degrees. The difference is called the spherical excess, and it grows with the size of the triangle. A tiny triangle near the equator barely notices this. A giant triangle whose corners touch the poles and the equator swells visibly with extra angle. This is not a trick of drawing. It is geometry listening to curvature. The sphere's positive curvature pushes geodessics gently together, and angles plump in response. Everyday experience quietly confirms this. Airlines plan routes that follow great circles, even when the line on a flat map looks strangely arched. Sailors have long known that a steady compass course, a rum line, does not give the shortest passage. It creates a spiral that crosses every meridian at the same angle. The quickest route is a great circle that changes its compass, bearing over the journey, a path that can feel counterintuitive until the globe is held in the hands and the path traced with a finger. Navigation, at heart, is a conversation with curved rules. Now turn the fabric the other way and the tone changes. Imagine a surface shaped like a saddle. Rise along one axis, dip along the other. This is a window into hyperbolic geometry, where curvature is negative. On this surface, geodessics spread apart more than they would on a flat plane. Triangles look slim, and when their interior angles are added, the total is less than 180 degrees. The larger the triangle, the greater the deficit. Space feels roomier in a way that thought can sense, even if the eyes cannot easily picture an infinite saddle. Wander a little farther, and a striking property appears. In a flat world, through a point not on a line, there is exactly one line that never meets the original. On the saddle-shaped world, there are infinitely many that never meet it. The notion of parallel blossoms into a whole fan. Lines that start almost together drift apart as they go, like companions strolling on diverging paths that both feel straight under their feet. A circle on this surface encloses less area than a flat circle with the same boundary length, because the space inside seems to pull away, creating additional room around everything. Even simple grids refuse to behave. Squares cannot tile the entire surface without bending and compromise, while rich tessellations with many-sided shapes fit with a pleasing inevitability. To see hyperbolic geometry clearly, mathematicians use models that bring the infinite within reach. One elegant model is the Poincaré disk. Picture all of the hyperbolic world packed inside a circle. The circle's boundary is not a wall one can touch. It represents points infinitely far away. The straightest lines in this picture appear as arcs of circles that meet the boundary at right angles, or as diameters through the centre. Angles are drawn faithfully, which gives the eye a true reading of shape at each point, even though distances compress more and more near the edge. A triangle near the rim looks small and sharp. In the hyperbolic world, it can be large and wonderfully thin. Another model, the upper half plane, shows the same ideas on the set of points above a horizontal line. There, geodessics are semicircles that meet the line at right angles, or vertical rays that rise straight up, and again the boundary line marks an unreachable infinity. In both pictures, the models do not pretend that everything is as in the hyperbolic world. They preserve angles perfectly, but trade away uniform scale to make the overall structure visible. These models do more than tame abstraction. They allow patterns to be drawn, repeated, and admired. Artists have used them to craft delicate tessellations where fish, birds, or ornamental shapes shrink toward the boundary in endless ranks, each shape congruent in the geometry of the surface, even though the eye sees them getting smaller. The mind delights in the paradox, forever repeating, forever receding, forever faithful to the rules of an unfamiliar space. Curvature has practical echoes wherever there is a need to measure the world. Every map of the globe must make peace with distortion, because a sphere cannot be unrolled onto a plane without stretching or tearing. Some projections preserve angles, making compass bearings simple but inflating areas near the poles. Others preserve area but distort shape, softening angles into curves. None can keep everything perfect at once. The reason traces back to an intrinsic property. Curvature belongs to the surface itself and does not depend on how it sits in space. No trick of folding or smoothing can turn a positively curved world into a perfectly flat one. Peel an orange and try to press the peel flat. Cracks appear, and the peel insists on its own character. For navigation, the tension between curved earth and flat chart has long been a companion. A sailor or pilot chooses what to preserve and what to accept as a compromise. If the path must keep a constant compass direction, a special projection makes that path a straight line at the cost of exaggerating size far from the equator. If shortest distance matters most, a different chart shows great circles clearly while sacrificing other niceties. Instruments, tables, and later algorithms grew up around these choices, practical tools born from gentle arguments about curvature. All of this returns to a simple intuition. The space between points can carry its own mood. On the sphere, paths lean together and enclose more angle. On the saddle, paths lean apart and shave angle away. The feeling of straightness comes from walking without turning, not from the picture in a flat mirror. In curved spaces, even the concept of parallel gains local flavour. Two geodesics may start in harmony, and then part like a duet that resolves into separate lines. Circles do not behave as expected, and the circumference tells a slightly different story about the space it lives within. There is a quiet satisfaction in learning to read these moods. Place a triangle on a globe and feel the extra angle. Imagine a triangle in a saddle and sense the angle gently reduced. Picture the Poincaré disc and watch lines become arcs that still meet neatly at true angles. Picture the upper half plane and watch semicircles rise like lanterns, honest to the rules of their world. The metaphors help. A fabric that stretches and shrinks under starlight, shaping the journey of any traveller who moves across it. The facts do the gentle work. In one case, curvature is positive and geodessics tend to converge. In the other, curvature is negative and geodessics prefer to diverge. What begins as a curiosity becomes a way of thinking. Instead of asking only what shapes look like, the mind asks how space itself behaves. Instead of assuming that one set of rules fits everywhere, it learns to listen for the sound of the fabric underfoot. In that listening, familiar theorems reveal their local roots. This sum of angles in a triangle, once recited as a universal truth, turns out to be a statement about the character of the surface beneath it. Lines once imagined as eternal companions show that companionship depends on the world they inhabit. Curved rules invite a deeper question. Whose curves? Picture walking a path in thick fog. The ground underfoot feels smooth and familiar, yet the view is only a few steps wide. Walk long enough, and a strange comfort unfolds. The path returns to the starting place without a single turn marker. Locally, every stride seems straight and ordinary. Globally, the world quietly looped. This is the gentle idea of a manifold. Up close, space can look flat and rule-abiding. Step back in imagination, and the whole can surprise. The lesson is soothing and profound. The character of a place is not only in what a small patch reveals, but in how all the patches stitch together. A manifold is a space that in tiny neighbourhoods resembles ordinary flat space. Think of an ant exploring the surface of a smooth orange. Each small patch is nearly flat to the ant's tiny feet. Angles behave as expected in the ant's brief stroll. Yet the total surface is curved into a sphere, and a very long walk would reveal that there are no edges, only a round completeness. This blend of local familiarity and global personality makes manifolds perfect for thinking about the actual universe. They let the mind honour ordinary experiences, straight roads, square rooms, steady angles, while still allowing the grand shape of everything to be something more than a gigantic flat floor. Once local and global are separated, gentle questions become possible. Could space be infinite, stretching without bound in every direction, with no edges at all? Could it be finite yet still edgeless, the way the surface of a sphere is finite but has no border to fall off? Edges are not required for a space to end. A loop can be complete without a cliff. In a finite, edgeless world, a traveller who keeps going may eventually return, not because a wall turned the path, but because the path wraps through the fabric itself. In an infinite world, the path never repeats, and any loop must be chosen deliberately. Topology gives language to these possibilities. Topology cares about how a space is connected rather than about exact distances and angles. Two shapes can be topologically the same if one can be stretched into the other without tearing or gluing. The surface of a coffee mug with a single handle can be stretched into the shape of a donut because both have one hole. They share a topological fingerprint. Geometry and topology cooperate like tempo and melody. Geometry sets local rhythm, distances, angles, curvature. Topology writes the global tune, holes, loops, connectedness. A space can be locally flat in the geometric sense and still globally folded by its topology. With that in mind, picture three calm possibilities for the universe's spatial shape in broad strokes. One possibility is positive curvature, like the three-dimensional analogue of a sphere. Such a space can be finite and without edges. Keep travelling, and a grand loop might eventually close. A second possibility is zero curvature, a flat geometry that can be infinite, like an endless Euclidean room, or finite if the room is wrapped on itself in each direction to form something like a three-dimensional torus. In that wrapped version, move straight ahead, and the journey quietly re-enters from the opposite side, as if reality were a game with seamless wraparound. A third possibility is negative curvature, a hyperbolic mood in 3 dimensions. These spaces can be infinite, and some can be finite without edges if they are carefully and consistently identified, like intricate quilts whose seams line up. None of these pictures require speculation about exotic materials. They're calm, mathematical ways a manifold can be arranged. If space were multiply connected, wrapped on itself, subtle signatures could appear. Light could take more than one loop to reach an observer, offering repeated views of the same distant structure from different directions and at different travel times. Patterns written into the oldest light might echo with telltale symmetries, like a melody that comes back in a new key. The idea is as gentle as it is striking. Topology can leave fingerprints, and those fingerprints ride on beams of light. Light is the universal messenger, and measuring the shape of space often means listening to light with care. 2 families of tools help: standard candles and standard rulers. A standard candle is a source whose intrinsic brightness is well understood. Compare how bright it appears to how bright it should be, and distance can be inferred. A standard ruler is an imprint of a known size stamped into the sky, not as a physical yardstick, but as a statistical feature. One such ruler is the scale imprinted in the clustering of galaxies by ancient sound waves that once rippled through the hot plasma of the young cosmos. That characteristic scale, often called a baryon acoustic feature, tends to show up as a preferred separation between galaxies. Measure its apparent size at different depths of the sky, and the cosmic geometry begins to reveal itself, because curvature influences how angles, distances, and brightness relate. The oldest light, the cosmic microwave background, provides a delicate canvas for this listening. It is a bath of microwave photons released when the universe cooled enough for light to travel freely. It carries a faint speckled pattern, tiny temperature variations that grew into today's large-scale structure. The typical angular size of certain features in that pattern depends on geometry. In a flat space, the features subtend a characteristic angle. In a positively curved space, light paths bend inward, and the same physical scale appears larger on the sky. In a negatively curved space, light paths spread, and the same scale appears smaller. By comparing the measured angular patterns to the expected physical scale, one arrives at a quiet statement about global geometry. The large-scale universe appears very close to flat, within current sensitivity. That sentence is calm and cautious, because measurements always come with uncertainties, but the mood is steady. The distinction between the observable universe and the entire universe also matters. The observable part is the region from which light has had time to arrive since the cosmic clock started. It has a horizon set not by a wall, but by time and expansion. Beyond that horizon, there may be more of the same, or new topological twists waiting out of view. The absence of edges in observation does not prove infinity, just as returning to a starting place does not prove finiteness. It means only that within the fog-lit circle of the observable, the path is smooth and complete. Relativity enters softly as the rulebook that lets geometry converse with physics. In this view, space and time merge into spacetime, a 4-dimensional manifold equipped with a metric that tells how intervals are measured. Curvature becomes not a decoration added after the fact, but the very expression of gravity. Matter and energy influence the curvature of spacetime. In return, that curvature guides the motion of matter and light along geodesics, the straightest available paths in that curved arena. A beam of light bends near a massive body, not because a force reaches out and tugs it, but because the geometry near the mass is shaped so that straight paths are deflected from the perspective of a distant observer. The calm equation often quoted in Spirit says it neatly: matter tells spacetime how to curve, spacetime tells matter how to move. Curvature can be sensed in many quiet ways. Starlight that passes near a galaxy may arrive as 2 or more images, a natural lens shaped by geometry alone. Time runs slightly differently near massive bodies, a fact that precision clocks register without fuss. Planetary orbits precess by tiny amounts, which sensitive observation accumulates into certainty. Gravitational waves ripple through space-time when massive bodies dance, and detectors register their passing as minute changes in measured lengths. Each of these observations is a small whisper, and together they hum the same tune. Geometry is not only the stage, it is an actor. Viewed through this lens, the shape of space is both a global question and a local practice. Globally, topology decides whether paths loop, whether there are hidden shortcuts, whether infinite extension is real or merely apparent. Locally, geometry decides how rulers tick, how angles add, and how light bends. The universe may be nearly flat in its large-scale geometry, yet still playful in its topology, in ways too subtle to have shown themselves. Or it may be simple and open, a tranquil expanse where every straight path continues forever without returning. Either way, the language of manifolds allows the mind to carry both certainty and openness at once. Return to the foggy loop for a final restful thought. Whether the path closes or runs onward, the ground beneath is consistent in small steps and expressive in long arcs. Light traces those arcs faithfully. Rulers and candles in their different ways consult the same geometry. And wherever mass and energy gather, the fabric shapes around them, guiding travellers and photons with equal courtesy. This is the comfort and the wonder. Emptiness can be structured without being crowded, and the map to that structure can be read in the soft glow that reaches every night sky. If mass tells space how to curve, even nothing takes a shape. Imagine a slow river winding through a quiet valley. Leaves resting on its surface, not being pulled by invisible strings. They are simply following the water's natural flow. Gravity, in Einstein's picture, is like that river. Objects drift along the geometry of space-time, taking the straightest available path through a landscape that can bend and swell. The tug once imagined as a distant force becomes the shape of the channel itself. Before this view, gravity lived in the language of forces. In the Newtonian story, two masses attract one another across empty space, and the strength of that attraction depends on how massive they are and how far apart they sit. It works beautifully for falling apples and circling planets, and it still guides a great deal of engineering. Yet one puzzle lingers in the background. Why should a force act across a void with no mediator? Einstein's insight eased that worry. Instead of forces reaching across empty space, space-time itself carries structure, and free-falling bodies trace out geodessics, the straightest possible paths available in that curved structure. In free fall, the sensation of weight disappears because no force presses. The path simply follows the river's current. To make this precise without losing the calm, imagine that measuring distance and duration is not an afterthought, but the heart of the story. A metric is the rulebook that tells how to calculate the interval between events, blending space and time into a single measure. In everyday life, distance and time are separate. In space-time, they are woven. The metric acts like a soft grid that says how rulers tick and how clocks count. When mass and energy are present, that grid is not perfectly even. It dips near a star, swells near a void, and its gentle unevenness is what is called curvature. A geodesic is then the path that locally extremises the interval, no sideways push required. A planet circling a star is not continually yanked into a turn. It glides along a natural groove in space-time's shape. Light brings a special kind of clarity because it sets the ultimate speed limit. At any event, any point in space-time, one can imagine a light cone, the slender region that marks all the directions light could move next. Inside that cone lie all the possible motions for anything that respects the speed limit. Outside it, motion would require faster than light travel and is simply not available. Near massive bodies, The local structure of these cones changes their tilt and their opening just enough to matter. Time itself stretches slightly in stronger gravity. Clocks deeper in a gravitational well tick more slowly, and a beam of light climbing out loses energy, shifting to a redder hue. None of this is dramatic to the senses, but precision instruments record it faithfully, and careful experiments have stacked up the evidence like smooth stones. When light passes near a massive galaxy or cluster, its path bends in the same way a leaf bends around a gentle whirl in the river. This bending is not due to a force tugging on the light. Light has no mass to pull. Instead, the space-time geometry near the mass is shaped so that the straightest path is not the Euclidean straight one an artist would draw on paper. The result is gravitational lensing. A single distant galaxy can appear as multiple images, or as an arc, or as a ring if the alignment is just right. The universe becomes its own lens, sketching curves where straight lines would otherwise have been. This effect does double duty. It confirms the geometric nature of gravity, and it reveals what would otherwise be hidden, allowing mass to be weighed even when it is dark. The river picture helps in another way. Consider an elevator in free fall. Inside, a dropped object hovers and drifts as though no gravity exists, because elevator and object share the same geodesic for a moment. Step outside that small region, and differences appear. Two nearby leaves may start side by side, but drift apart or together, depending on how the river bends. In space-time, this relative drift is tidal gravity, the gentle clue that curvature is present. Gravity can be locally made to vanish by free fall, but curvature cannot be transformed away. It shows itself in the changing relationships among nearby paths. A calm summary takes shape. Gravity is geometry. The metric tells rulers and clocks how to behave. Geodesics guide free-falling bodies the way currents guide leaves. Curvature encodes the presence of mass and energy, and reveals itself through tidal effects, time dilation, and the bending of light. What once looked like action across a gap becomes a conversation between matter and the shape of space-time. The conversation is steady and polite. Matter arranges the fabric. The fabric conducts everything along its quiet lines. This viewpoint does not crowd space with machinery. It simplifies. Where earlier stories required a force reaching across emptiness, the geometric story asks only for a rule of measurement, and the willingness to let that rule vary gently where mass and energy live. In regions far from heavy bodies, space-time relaxes toward flatness, and the old Newtonian approximations return, useful as ever for planning orbits and building bridges. Nearer to compact objects, the curvature grows, light cones lean, and the differences become too clear to ignore. Precision clocks feel the stretch. Starlight curves enough to betray hidden mass. Ripples in the fabric, sent by colliding bodies, travel outward and subtly lengthen and shorten distances as they pass. Hold the image of the slow river a moment longer. Leaves do not struggle to know the way. The water carries them. In the same spirit, planets, photons, and even passing ripples follow the geometry at hand. Once the shape is known, the motion is no longer mysterious. It is graceful, and it is inevitable. Zooming in, the vacuum is not empty at all. Picture the vacuum as a night ocean under a thin moon. At first glance, it looks perfectly calm, a great black stillness stretching in every direction. Wait, and a different truth appears. Tiny ripples wrinkle the surface, then fade. Faint patterns rise and fall with no wind to push them. In quantum field theory, the vacuum is that ocean. Fields fill space even when no tangible particles are present, and what is called a particle is a localized excitation of a field, a little packet of disturbance that can be counted and measured. The ocean is never entirely still because the rules that govern it do not allow exact stillness. The bedrock is simple to say and subtle to hold. Every field has modes of vibration, much like a string has harmonics. In a purely classical world, those modes could all be turned down to absolute zero motion and energy. Quantum mechanics forbids that perfect rest. Because position and momentum cannot both be fixed with absolute precision, the field cannot sit exactly at the bottom of its energy well. There is always a residual jitter called zero-point energy. It is not a surplus of useful fuel waiting to be scooped up. It is the minimum hum consistent with the uncertainty built into the world. This hum is sometimes described using the language of virtual particles, but it helps to tread gently. Virtual particles are not tiny, short-lived marbles popping in and out of reality. They are a bookkeeping device inside certain calculations, the internal steps in a diagram that helps predict measurable outcomes. The vacuum's restlessness is real in its effects, but the particles that textbooks draw inside the math are not little objects one could bottle. They're a way to talk about how fields influence one another, even when no free detectable particles are present. A quiet, famous demonstration of vacuum structure is the Casimir effect. Imagine two very flat, uncharged, conducting plates held close together with a small gap between them. Electromagnetic fields can vibrate in many modes, but the presence of the plates restricts which wavelengths will fit in the gap, rather like a musical instrument that only allows certain notes. Outside the plates, more modes are available than inside. The difference in allowed vibrations produces a tiny pressure that nudges the plates toward each other. This attraction has been measured with great care. No new forces are being invented. The effect falls naturally out of how fields behave when boundaries are introduced. It is a gentle demonstration that the vacuum is a medium with structure, even when nothing obvious fills it. If the vacuum seethes, why does daily life feel calm and predictable? Partly because the ripples are tiny and rapid, averaging out over the scales of ordinary experience. The quantum jitter becomes noticeable only when experiments are arranged to isolate and amplify its effects, like the narrow gap in the Casimir setup or the delicate conditions in certain superconducting circuits. Another reason is that macroscopic objects are constantly interacting with their surroundings. The little correlated quantum excitations that matter for small systems are quickly washed out by countless interactions, a process often described as decoherence. The result is a world that, on human scales, looks classical and steady. The ocean is still a quantum ocean, but from the shore its surface looks smooth. Zero-point energy sometimes invites an extravagant question. If the vacuum has energy, could it be tapped like a hidden reservoir? The gentle answer is no. The vacuum state is already the lowest energy configuration available. Extracting energy requires falling to something lower, and there is nowhere lower to go. Practical quantum devices harvest energy by moving systems from excited states down to the ground state, not by mining the ground state itself. The vacuum's hum influences behavior, but it is not a bank account. The restless ocean leaves hints in other places too. In atomic physics, for example, interactions between the electron and the vacuum's electromagnetic field produce tiny shifts in energy levels, contributing to precise effects such as the Lamb shift. In condensed matter, engineered structures allow certain vacuum fluctuations to be shaped and redirected, leading to phenomena that can be measured and used in technology. Each case is a controlled conversation with the vacuum's ever-present ripple, rather than a wild storm. As thought walks towards smaller and smaller scales, a final careful image takes shape. At ordinary distances, space-time looks smooth, and the fields that live on that backdrop do their quiet work. As the scale shrinks, the energy associated with probing that scale grows, and the tidy separation between field on a calm geometry and the geometry itself becomes harder to maintain. Near the Planck length, often described as around 1 × 10⁻35 meters, classical ideas about space-time as a continuous fabric may break. Some approaches to quantum gravity suggest that geometry itself could fluctuate, that the very notion of a fixed distance might blur. These ideas are active research rather than settled fact, and they are mentioned here only to mark the shoreline. Beyond it, the map is still being drawn with patient hands. For now, it is enough to hold the picture of the night ocean, Fields fill every point of space. Particles are ripples that stand high enough to be counted. Even in the calmest state, the surface is not fully still. Uncertainty guarantees a trace of motion. The Casimir effect shows that when boundaries are introduced, the ocean's pattern changes in a way that presses lightly on matter. The world feels quiet because scales blur small jitters into smooth averages, and because interactions with the environment keep large systems steady and classical to the senses. Stand by the shore and watch the ripples gather and fade under the moon. Nothing dramatic is required to make them. Their source is the rule that perfect stillness is not allowed. That rule is neither ominous nor exploitable. It is simply the way the deep fabric of fields maintains its balance. Beyond shape, consider holes, loops, and connectedness. Thread a small bead onto a thin thread and set it drifting. If the thread passes through a loop, the bead cannot be pulled free without cutting the thread or breaking the loop. That is the mood of topology. Pay attention to which loops can be tightened to nothing, and which loops trap a bead no matter how gently you tug. Shape, in this view, is not about angles and lengths. It is about connectivity, holes, and what can be deformed without tearing. A friendly example lives in every kitchen. A solid coffee mug with one handle can be kneaded, in imagination, into a donut shape without cutting or gluing. The bowl stretches into the ring, the handle thickens into the donut's body, and the hole through the handle becomes the donut's hole. No new punctures appear and none are sealed shut. Topologically, the mug and the donut are the same because each has exactly one loop that traps a bead. A sphere, by contrast, has no such loop. Any band drawn on its surface can be shrunk to a point. Topology calls two shapes that can be deformed into each other through smooth, continuous motions homeomorphic. The recipe is simple. Stretch, bend, and squish are allowed. Cutting and pasting are not. Once cutting is forbidden, a new kind of measurement appears, one that does not budge when shapes are gently deformed. These are invariants. A very intuitive invariant for surfaces is the genus, a quiet count of how many independent holes a shape has. A sphere has genus 0. A donut has genus 1. Two donuts fused side by side have genus 2. Another powerful invariant is the Euler characteristic, a single number that, for many familiar surfaces, can be thought of as a balance between how many corners, edges and faces a shape can be divided into. For smooth closed surfaces, this number takes on calm, telling values: 2 for a sphere, 0 for a donut, -2 for a two-hole donut, and it continues in that steady rhythm. The exact formulas can be left sleeping. What matters is that these numbers remain steady through any amount of bending. They are the fingerprints of connectivity. This focus on holes leads to a new way of reading paths. Draw a loop on a shape and try to shrink it down without leaving the surface. On a sphere, success is guaranteed. On a donut, some loops shrink and some loops refuse. A loop that threads the hole traps the bead. Count how many times a loop winds around the hole, and you learn a winding number, a quiet integer that records a topological fact. The loop is not trivial, and no amount of gentle massaging will erase it. The world of knots grows from this habit, though knots add the extra spice of embedding a loop in space itself. Even without knots, the simple act of asking which loops can vanish and which loops persist teaches the hands to feel structure where rulers remain silent. The same ideas recur in fields and materials, where holes can be places where an orderly pattern breaks down in a way that cannot be smoothed away. In a superfluid or a very thin superconductor, the wave-like state of many particles carries a phase, an angle-like quantity that can be read along a loop. If the phase winds by a whole turn as you go round, you have a vortex at the centre, a topological defect. The circulation is quantized by that winding number. It is not a matter of energy minimization alone. It is a matter of connectivity. You can move the defect. You cannot erase it without letting two opposite windings meet and cancel, or without tearing the pattern. Crystals tell the same story in a different accent. Their atoms sit in a repeating lattice, but sometimes a row ends early, or an extra half plane of atoms cuts in. These are dislocations, tiny misalignments that cannot be healed by nudging neighbours slightly. The lattice would need to slip along a whole line to set things right. Liquid crystals, the kind found in many screens, display visible defects where the preferred direction of molecules twists and misaligns. Those points and lines act like topological charges, each labelled by how the local orientation turns as you walk around. Even hair on a sphere refuses to lie flat everywhere at once. Comb a sphere carefully, and a cowlick must remain. That tidy impossibility is a topological theorem in disguise. Topology even guides waves and electrons. In certain materials, electrons occupy states whose collective behaviour is organised by a topological index. Change the shape gently, roughen the edges, add a little disorder, the index does not care. As long as the material's essential energy gap stays open, special surface states remain, conducting along edges while the interior stays quiet. The technical details sit beyond this calm stroll, but the refrain is familiar. Count the right kind of nothing, holes in momentum space, windings in a mathematical map, and you predict robust behaviour that geometry alone would miss. Why does this counting of absence change understanding so much? Because connectivity constrains everything that moves, flows, or vibrates. Water in a perforated basin finds channels you cannot guess from a single measurement of width and depth. What matters is which paths connect where. A wave on a drumhead rings in patterns that depend on whether the drum has a central hole. A charge placed near a hollow conductor induces surface patterns that remember where space is available and where it is not, even though the interior is empty. In all these cases, the details of angles and lengths affect frequencies and intensities, but the gross features, the presence or absence of loops, decide what is possible in the first place. The bead-on-thread picture is a gentle companion for all of this. Slip the bead through a loop and it is captured. Thread it around a raised bump that does not go all the way through and it slides free. Topological questions ask, again and again, which captures are permanent under smooth deformations. Once answered, they grant guarantees. A vortex will not vanish on a whim, a dislocation will not melt away under small perturbations, an edge state will not disappear because a boundary was scratched. A soft recap brings the threads together. Topology watches what survives stretching and smoothing. Homeomorphisms certify when two shapes belong to the same connected story. Genus and the Euler characteristic give compact labels for that story. Defects in fields and matter are the places where global organisation refuses to be ironed flat. Their persistence is not bravado but bookkeeping. Counting nothing sounds paradoxical, yet it clarifies what must stay and what may change. It is a way of finding structure in silence. Patterns remain even when details fade. Symmetry. Hold a simple kaleidoscope up to a lamp and turn it very slowly. The colours rearrange, the shapes recompose, yet the mood stays the same. That steady calm amid change is the feeling of symmetry. In science, symmetry is not about decorative sameness. It is about transformations that leave the rules untouched. Rotate the stage, shift the scene, slide the clock's hand forward, and if the laws still speak with the same voice, symmetry is present. It is the grammar of emptiness, the quiet structure that remains even when scenery moves. Think first about space. If the rules of physics are the same here as they are a short step to the left, there is translational symmetry. If the rules do not care which way a laboratory is faced, there is rotational symmetry. If the rules are the same today as they were yesterday and will be tomorrow, there is time translation symmetry. These are not mere niceties. They let experiments be portable and predictions reliable. A pendulum does not need to be reinvented in each room. A beam of light behaves the same on the hillside as it does by the sea. A century ago, Emmy Nether noticed something deeply consoling. Whenever a system's behaviour is unchanged under a smooth family of transformations, there is a conserved quantity. The statement is precise in mathematics, but the essence is gentle enough to hold in the mind. If the rules do not change with time, energy is conserved. If the rules do not change when you shift your location, momentum is conserved. If the rules do not change when you rotate, angular momentum is conserved. Symmetry becomes a promise that certain measures will remain steady even as details swirl. In the kaleidoscope, the rearrangement of shards does not alter the pattern's deep balance. Noether tells us why some balances are inviolable. Not all symmetries live on grand stages like space and time. Some belong to the internal life of fields. In quantum theory, a simple field may be altered in a uniform way, its phase twisted by the same gentle amount everywhere, without changing any observable outcomes. That hidden sameness is a symmetry, and when the twist is allowed to vary from place to place, new structures enter, guiding interactions. These are the soft beginnings of gauge ideas, where the demand that local symmetries hold leads to the existence of fields that keep the book balanced. The vocabulary can grow technical, but the spirit is familiar. Insist on a certain invariance, and the world obliges by introducing a gentle mechanism that preserves it. Symmetry can also break, and the breaking can be creative. Imagine water cooling into ice. The liquid respects every direction equally. The solid chooses a pattern, selecting certain directions as special. The underlying rules didn't lose their symmetry, but the state of the system decided. A magnet provides the same lesson. Above a critical temperature, the little atomic magnets aim carelessly. Below it, they align, picking a direction in space and holding to it. This choice is called spontaneous symmetry breaking. From the decision, new behaviour emerges: rigidity, patterns, excitations that behave like new particles inside the material. What looks like a loss of freedom is actually a way the system finds stability and reveals new possibilities. The line between symmetry and structure runs through daily life as gently as frost through a window pane. Snow crystals form with graceful sixfold symmetry, each arm echoing the others because the lattice of ice repeats in a regular way. Crystals in minerals show repeating motifs that march through space, and the allowed symmetries constrain those patterns. Even simple laws we trust carry the signature of symmetry. The path of a thrown ball in a uniform gravitational field is predictable, because the rules are the same from place to place and from moment to moment. Keep sliding the problem in space or time, and nothing essential changes. Art and architecture read this grammar fluently. A colonnade that repeats its span invites a steady pace and a steady breath. A rose window revolves a theme around a centre, each rotation renewing the same design. Minimalist rooms use symmetry sparingly, letting one axis line up sight and air. The pleasure felt in such spaces is not an accident. The eye and the body recognise invariance and relax, trusting that a small change in viewpoint will not break the scene's promise. Even in music, a theme that returns with a rotation or an inversion reassures the ear that a hidden rule is being honoured. There's also the charm of near symmetry, where a pattern almost repeats but leaves a small deliberate deviation. The brain notices the rule first and the exception second, and meaning flows from the tension between them. Nature does this constantly. Leaves spiral with near regularity around a stem. Coastlines suggest fractal echoes without being perfect copies. Symmetry provides the baseline. Life plays the variations. In the silent background of all these examples, emptiness is being told how to behave. When the vacuum of a theory respects a symmetry, certain particles may remain massless or certain interactions may be forbidden. When the vacuum chooses a specific state, the same rules may now allow masses to appear or new interactions to show themselves. The stage is not a blank, it is a canvas with a preferred weave. The audience may not see the weave directly, but every movement across it is shaped by its invariances. A calm way to hold the whole picture is to return to the kaleidoscope. Turn it and the fragments tumble, yet the relation among mirrors keeps a strict covenant. That covenant is symmetry. It explains why some quantities stay the same regardless of the tumbling, and why certain arrangements are inevitable. When the mirrors are ever so slightly misaligned, broken symmetry, new images appear, and the eye delights in the fresh order. The grammar has not vanished. It has spoken a new sentence. A gentle recap. Symmetry means invariance under transformation. From that invariance, conservation follows by Noether's insight. When symmetry breaks, patterns emerge, and new behaviour becomes possible. The world around offers constant echoes: snow, crystals, balance in motion, balance in design. Symmetry is the quiet rule beneath both stillness and change, the reason emptiness can have character while remaining unfilled. Silence has design. So do empty rooms. Think of a sheet of paper with a single brushstroke crossing it. The stroke is bold, but the hush around it does the real work. That quiet border, the white margin that lets the picture breathe, carries the weight of meaning. Emptiness is not a lack, it is a frame that steadies attention. In visual art, this hush has a name: negative space. The eye does not only read the dark ink, it reads the intervals that hold the ink in place. Painters and designers use negative space the way musicians use rests. A figure is outlined not just by its edges but by the shapes of the gaps around it. A leaning tree gains grace because the sky peeks through its branches. A simple logo feels precise because the field around it stands still. Gestalt psychologists noticed long ago that figure and ground trade places as the mind plays. A vase becomes two faces become a vase. The lesson is gentle and powerful. What is not drawn can be just as informative as what is drawn, and the border between them is where perception wakes up. In Japanese aesthetics, there is a related idea called ma. The word points to an interval, the space between things, the pause that allows one event to be felt before the next arrives. In a sequence of doors, ma is the small courtyard that lets light pool and feet slow. In a line of notes, ma is the lingering echo that allows the melody to land softly. It is not simply emptiness, it is a charged pause, an active, living gap where meaning collects. On paper, a calligrapher leaves ma around the character not by accident but by design. The character breathes because the paper is allowed to remain paper. Minimalist architecture takes this intuition into walls and air. Instead of ornament upon ornament, there is a trust in proportion, light and surface. A quiet room with clean lines and a generous threshold does not lecture the visitor. It invites the body to unclench. Tadao Ando's poured concrete planes, for example, use daylight like a material, cutting simple seams that let the sky write lines on the floor. Mies van der Rohe's famous phrase about less being more captures a cousin to this thought. When the number of elements is reduced, their relationships can sharpen. White ceilings, long sight lines, and uncluttered corners lower the brain's constant need to resolve busy patterns. Visual noise drops, attention stops scattering. Silence has a geometry in sound as well as in sight. Rooms carry a reverberation time, a measure of how long a sound lingers before it fades into the background. A space with hard, reflecting surfaces can blur speech into a wash. A space with soft, absorbent surfaces can swallow sound too quickly and feel oddly airless. The humane middle is rarely accidental. Museums, chapels, and libraries are tuned with materials, wood, fabric, textured stone, so that footsteps become soft and voices turn to murmurs without being smothered. Monasteries learn this by experience. A cloister walkway wraps a courtyard and becomes an instrument. It slows the mind by slowing the echo. Even an ordinary living room can be adjusted by a rug and a heavy curtain, small tools that carve out islands of acoustic calm. Museums offer a special case of the geometry of pause. A painting hung cheek by jowl with others drowns. A painting given a simple wall, and a few arms' lengths of air starts to speak. Curators stage long sight lines to a single sculpture at the end of a corridor, or they break a sequence with a bench in a patch of light. The so-called White Cube Gallery, for all its critics, understands a basic truth. Less surrounding information means the signal can stand up straight. Temples and shrines work along similar lines but with a different mood. A Torii gate frames nothing but air and trees. The frame tells the body that a transition has happened. A Zen garden rakes gravel into waves, and the emptiness between the stones supplies the sea. In Islamic courtyards, a rectangular pool lays down a calm mirror where sky and geometry whisper to one another. In each case, emptiness is not a void, it is a medium. How does this space guide feeling? Part of the answer is physiological. The brain is a prediction engine that tires when it must resolve too many competing signals. Empty regions simplify the scene, letting the attentional spotlight rest. Edges and alignments become easy to follow, depth cues clarify, scale becomes legible. Another part is learned. Culture teaches what to do with a pause. A quiet foyer says, wait. A low ceiling says, move along. A long nave says, look ahead. The cues are gentle, but they shape posture and breath. A white margin around text makes reading less effortful. A margin around an object makes seeing less effortful. Designers use a few dependable tricks. Frame a view and the view grows in meaning. Lower the ceiling near an entrance and raise it beyond, and the body feels release. Keep a palette restrained and a single colour becomes vibrant. Align a table with a window, and the mind understands order without being told. None of these rules requires luxury. They require the courage to leave space unfilled and the patience to let small proportions do large amounts of work. The link back to the sciences is almost shy. In physics and mathematics, emptiness is not a blank but a set of permitted relations. In a well-designed room, the emptiness between chair and window is a permitted relation too. A channel for sight, a path for light, a corridor for moving air. In acoustics, the shape of the gap decides which frequencies are hushed and which are amplified. In perception, the amount of white space around an object changes how quickly it is recognized. A laboratory echo of the figure ground play that artists have known in practice for centuries. Even the humble margin on a page is a small engineering choice. It lifts cognitive load the way a well-shaped culvert lifts floodwaters away from a path. Think again of the white margin that lets the picture breathe. It is a small act of restraint that pays a large dividend. The brushstroke becomes confident because it is not crowded. The visitor becomes calm because the room is not noisy. The ear hears a whisper because the rest of the sound has been dimmed. Emptiness, treated with care, becomes a resource. There is a quiet pleasure in recognizing how many disciplines have learned this in parallel. Painters, monks, architects, and acousticians have all, in their own language, drawn the same conclusion. Space is a partner. Leave it room to act, and it will distribute attention, soften edges, and invite reflection. That invitation has a shape, even when nothing visible occupies it. It is a corridor of possibility, a breathing pause that lets meaning arrive on time. So, does nothing have a shape? Hold up a blank canvas. The surface looks empty, yet the frame fixes its edges, the weave gives it texture, and the light falling across it sets a mood. The picture is absent, the conditions for a picture remain. That is a gentle way to approach the question. Does nothing have a shape? The answer depends on what is meant by nothing, and different disciplines mean different things. Mathematics begins with structure. Geometry is not a free-floating idea. It requires a stage equipped with relationships. A space in mathematics is given rules for distance, angle, or at least for which points lie next to which. Without such rules, there is no talk of straightness, curvature, or dimension. A pure, propertyless nothing cannot host a metric, cannot define a line, and cannot measure a distance between 2 points because there are no points to consider. In that sense, the phrase shape of nothing is empty by design. Where there is truly nothing, there is nothing to shape. Yet mathematics is comfortable with very sparse structures that feel close to empty while still being lawful. The empty set is a legitimate object, but it is not a place. A topological space can be defined with minimal data that tells which sets are open. With just a bit more, one can add a metric that measures distances or a differentiable structure that allows smooth curves. These layers are choices. Add them, and geometry wakes up. Refuse them, and geometry does not apply. When mathematicians speak about the geometry of a manifold or the curvature of a surface, they are speaking within a world where something, points and relations, already exists. The structure is the frame. Shape is the way the frame behaves. Physics uses the same word, nothing, but usually means the vacuum. In modern field theories, the vacuum is not a barren absence. It is the lowest energy state of fields that fill space. Those fields are permitted to fluctuate in restrained ways, and their interactions are tightly choreographed by symmetries and conservation laws. Even in a region cleared of matter and radiation, the possibilities encoded by the fields do not vanish. The vacuum can have different phases. Much like a liquid and a solid are phases of the same substance. It can break symmetries and thereby endow particles with properties. It can admit boundary conditions that nudge phenomena like the tiny Casimir force. None of this should be mistaken for a bubbling stew of particles in the ordinary sense. It is subtler. Rules without actors, readiness without events. Because spacetime itself has geometry, the vacuum inherits further character. In general relativity, empty regions are described by metrics that solve the gravitational field equations with little or no matter present. Flat Minkowski spacetime is a simplest example, a calm grid where light cones stand upright and rulers agree. There are also curved vacua, such as de Sitter space with positive curvature, or anti-de Sitter space with negative curvature, each with its own causal structure and horizon behaviour. These are not decorations painted on top of nothing. They are the statement that geometry can exist even where matter is absent. That is not nothing in the strict philosophical sense. It is an arena with rules, a canvas without a painted scene. Philosophy asks for care with words. When ordinary language says nothing, it often means no particular thing around here, as in nothing is in the box, which still assumes the box, the air, the light, and the rules that make boxes possible. If nothing is taken literally, no space, no time, no laws, no possibilities, then questions about shape, duration, and position become misplaced. Shape is a relation among parts within a space. If there are no parts and no space, the question dissolves. This is why earlier philosophers sometimes treated talk of true nothingness as either incoherent or purely conceptual, a negation used for contrast rather than a describable state. Language itself tempts confusion by letting a word like nothing behave grammatically like a name, when it is mainly a way to deny. A calm synthesis keeps both strictness and usefulness in view. If nothing means a complete absence of entities and relations, then it cannot have a shape, because shape is a property, and there is nothing to bear it. If nothing means a region without matter, then geometry can certainly live there, and fields can carry rules. In that practical scientific sense, empty space can be curved, can host waves, can lens light, and can store energy in subtle ways. What looks like nothing to the senses still has a frame, and that frame can be measured. The phrase, shape of nothing, then becomes shorthand for shape of the arena when no actors stand on the stage. The metaphor of the frame is helpful here. A bare canvas has edges, tension, and grain. The whiteness is not infinitely blank. It reflects light. It accepts pigment. It resists tearing. Similarly, a gravitational vacuum has a metric with a particular signature. a pattern of light cones that dictates which events can influence which. A quantum vacuum has a spectrum of allowed fluctuations shaped by symmetries and boundary conditions. These features are not add-ons, they are what make prediction possible. Remove them, and before and after lose meaning along with near and far. With them, experiments can speak and observations can be arranged. This perspective also softens the drama around the word. Much of what is most striking in modern physics involves the behaviour of apparent emptiness. Bending of light near a galaxy, expansion of large-scale space, tiny shifts in atomic energy levels, all are dramas played by the frame itself. The scene can move even when the stage looks bare. There is a quiet wonder in that. It means that absence can carry a logic, and that logic can be listened to. It is natural to ask whether this frame is fundamental or emergent, whether space and time themselves are basic ingredients, or long wavelength behaviours of something deeper. Some approaches to quantum gravity suggest that geometry could arise from more primitive relations, that distance might be a summary of entanglement patterns, or that space-time could be stitched from discrete building blocks that blur together at large scales. These are active ideas, not settled doctrine. Mentioning them here serves only to mark a boundary between what is well mapped and what is under exploration. Wherever the exploration leads, the earlier distinction will remain useful. A strict nothing cannot be shaped, an empty arena can. Hold the initial image once more. The canvas is blank and yet the frame exists. The grid of threads in the fabric gives direction. The light and the air give context. What can be painted is constrained by these quiet facts. If the word nothing means this sensitively prepared openness, then its shape is the pattern of constraints that remain when objects are absent. If the word means the absolute denial of being, then there is nothing to say. From the smallest quivers to the widest quiet, stand at the edge of a calm sea under starlight and watch the tide slip back. Take a step forward, and the shoreline eases away again, always a few quiet paces beyond. Cosmic expansion carries a similar feeling. Galaxies are not flying through a pre-existing emptiness into some larger outside space. Instead, the distance between faraway galaxies grows because the metric that measures distance is changing. Space itself stretches. A useful picture is not a ship sailing into a dark bay, but the spacing between ripples widening across the whole water. No centre needs to be singled out. Every distant patch sees the others recede, gently and all at once. That distinction softens a common worry. If space is expanding, what is it expanding into? Nothing extra is required. The geometry evolves according to its own rules, and the yardsticks used to compare far points slowly lengthen. Locally, motions remain ordinary. At a kitchen scale, atoms sit where they always sit, bound by forces that easily outrun the slow drift of expansion. Even within galaxies, gravity gathers stars into coherent swirls that hold together. It's only across vast gulfs that the stretching becomes noticeable, and even there it is patient rather than dramatic, an almost imperceptible change hardly felt in a human lifetime. Because light takes time to travel, the expanding sea of space writes horizons into the sky. One is a horizon of the past. Light from regions beyond a certain distance has not yet had time to arrive, so the observable universe is a sphere not of walls but of time. Look outward and backward together. The farther the gaze, the younger the light. The cosmic microwave background is the earliest page currently legible, a faint afterglow from when the universe became transparent and photons could move freely. Another horizon is more subtle and belongs to the future. In an ever-expanding universe there can be events so distant that no beam of light launched today will ever reach them. That boundary is an event horizon, not because something dramatic happens there, but because causal contact is gently denied forever. Horizons are not fences erected in space. They are relationships between distance, time, and the pace of expansion. A quiet question arises: what sets that pace? Observations show that On the larger scales, the expansion is not merely continuing, but accelerating. The simplest way to describe this within general relativity is to include a cosmological constant, a uniform energy density associated with the vacuum. Its effect is not to push with a wind, but to slightly alter the geometry so that large-scale distances grow ever more quickly. In that sense, the vacuum has a faint buoyancy. Care is helpful here. This uniform energy is not a reservoir to be tapped, nor is it a froth sending particles into being. It is a parameter in the gravitational field equations that fits many observations well. Other explanations exist in theory, but the constant is the calm, minimal way to say what the sky appears to be doing. These statements lean on patterns read from light. Standard candles, such as supernovae of a certain type, reveal how brightness dims with distance in an expanding geometry. Standard rulers, imprinted in the large-scale clustering of galaxies, reveal how a known scale appears in angle. The oldest light, with its delicate speckle, adds a third voice, because its characteristic features project to the sky differently depending on curvature. When those measures are read together, a quiet picture emerges. Spatial geometry looks very close to flat across the observable universe, within the reach of current sensitivity. That leaves a range of possibilities. A perfectly flat infinite space is compatible. A nearly flat but finite space that wraps on itself in subtle ways is also compatible, provided the wraparound size lies beyond what current surveys can reveal. Negative or positive curvature cannot be entirely excluded if small and cleverly arranged, but large departures seem disfavoured by the way the sky arranges its patterns. Even when global shape remains an open page, the local script is legible. Light passing near a massive cluster bends into arcs and rings, a lens drawn by geometry rather than glass. Background galaxies appear in multiple images, each one a path through a space-time that bows ever so slightly in the cluster's presence. On the grandest scales, galaxies drift apart with the flow, but their internal structures evolve in a quieter tug of gravity, gas cooling and starbirth. The emptiness between them keeps expanding, and yet that emptiness remains a lawful medium, with horizons that set what can be seen and when. Infinity itself is a word that deserves a soft touch. Space may extend without bound, or it may close on itself beyond the reach of current light. Either way, the observable part is finite for simple reasons. Light has only had so long to travel. The horizon is a moving shoreline. As time passes, more of the early universe becomes visible even as some distant regions slip beyond future contact. The picture is not static, and yet it is serenely patterned. Distances change, but the rules that choreograph the change are steady enough to guide prediction and to make sense of the sky's map. Vacuum energy sits at the crossroads of the tiny and the vast. Quantum fields suggest a baseline hum, while gravity hears something like a uniform pressure. Reconciling those scales is an open, delicate task. For this calm walk, it is enough to remember only the part that is well tested. A small, positive, uniform term in the cosmic bookkeeping fits the accelerating expansion and harmonizes with other measures of the large-scale structure. The number attached to it is not guessed from first principles here. It is inferred from the sky's own handwriting. Return to the shoreline. Each step into the shallows brings a new retreat of the line where water meets sand. The receding does not imply a larger sea beyond the sea. It means the tide's relation to the shore is changing in time. In the same way, the recession of galaxies is not a dash into an outside. It is the ongoing rescaling of the distances that relate them. The poetry of the scene is matched by its precision. Telescopes and surveys turn metaphor into measurement, yet the feeling remains. A quiet invitation to keep walking, knowing the edge will always be just ahead. A restful ending does not claim more than it should. The expansion of space is the story the light tells. Horizons mark what is observable, not what exists. A simple cosmological constant presently describes the acceleration well. though deeper explanations are possible and welcome if nature supplies them. The large-scale shape appears nearly flat across the part we can see, with room in the margins for subtle global topologies that lie beyond current reach. Emptiness in this picture is not a void without rule, but a medium whose rules are gentle enough to read and strong enough to trust. Let these shapes of silence settle. Begin with a breath, and let a simple thread run back through the night. Numbers gave a quiet mark for absence, a 0 at the still centre from which distances radiate. Lines and planes offered a clean grammar for position, the calm cross of axes making emptiness legible. Curves arrived to remind that straightness depends on the fabric, spheres plumping the angles of triangles, saddles slimming them down. Spacetime gathered these ideas and softened gravity into geometry, a river of intervals that guides planets and light. The quantum view hushed the stage further, showing fields at rest that nonetheless tremble, with a small, unavoidable ripple. Topology stepped in to count what stays when shapes are stretched, the loops that trap a bead, the holes that make a donut different from a sphere. Symmetry whispered its promises. When the rules remain the same as scenes shift, certain balances never break. Art and architecture translated those promises into rooms and margins, where designed emptiness lets forms speak. Finally, the cosmos widened, and the shoreline of the observable eased outward and away, expansion carrying the horizon like a tide. The central note is gently steady. Rules and relationships can describe even almost nothing. Give a stage only the lightest structure, a way to count, a way to compare, a way to connect, and the mind can trace the outline of silence without filling it. A frame exists even when the canvas is bare. The weave still guides the hand. Understanding that frame does not crowd the world, it clears it. Emptiness becomes a partner, not a void to fear, a medium where shape can appear and meaning can settle. Carry that with you into tomorrow's rooms and paths. Notice how a margin calms a page, how a pause gives a sentence weight, how a window orders a view without adding a single object. The same clarity that lets light tilt near a star is at work when a simple hall sets shoulders at ease. In learning the geometry of nothingness, attention learns to rest on what is present and what is absent, equally and kindly. If this quiet journey was soothing, there are more gentle explorations nearby. Other slow walks through ideas that turn the noisy world down and let curiosity move at the pace of sleep. You're always welcome to return, to listen, and to drift. May parallel lines finally meet, in dreams, where rules are patient and angles are kind. Until then, let the day loosen its grip, let thoughts settle like dust in a beam of moonlight, and let the hush of the frame carry you the rest of the way. Good night.